Alright, so this video is going to focus on balancing equations, balancing equations for formulas, and then also the writing the formulas and balancing the equations once those formulas have been written. So you always want to make sure you have proper formulas, which is why I really want to make sure that you're comfortable with the compound nomenclature that I discussed in the previous video. Once you get the formulas written, you always want to make sure you count your atoms and that you use coefficients, not subscripts, to make the number of atoms of each element on both sides equal. I encourage you to hold off on hydrogen or oxygen, as well as any other atoms that you find in multiple parts of the reactants or products. Think about it like a seesaw. If it's only in one reactant and one product, that's pretty straightforward to balance. But if it is in multiple reactants or multiple products, there's a little bit more hemming as to which one to change. So it's kind of better to treat those at the end once everything else has been balanced. They tend to resolve themselves. If you recognize you have a polyatomic that is present on both sides of the equation, you may treat that as a single unit. And then I always recommend you go back through and double check your counts that everything has equaled out and your equation is indeed balanced. So the first one we're going to look at here is KClO3 making KCl and O2. We have one potassium and one chlorine on both sides of the equation. We have 3 oxygens on the reactant side and 2 on the products. 3 and 2 do not equal out, and the next number that's greater than 2 and 3 that would make them have a common factor is 6. So to get them both to 6, I would need to multiply KClO3 by 2 and the oxygen by 3. Those are your coefficients, so that you have 6 oxygen atoms on both sides of the equation. Because you had to increase the amount of KClO3 on the reactant side, your Ks and your Cls are no longer in balance. But that can be handled relatively easily by just doubling the K and Cl, and you now have a balanced equation. This one looks a little bit harder than it really is. If you notice, you have polyatomics on both sides of the equation. You have NO3s and you have SO4s. So you can treat those as units. If we start from left to right and look at PV, we have 1 PV on both sides, so that part's okay. We have 4 NO3 ions on the reactant side, and we have 2 on the product side. So we're going to need 2 of the calcium nitrate molecules. We have 1 calcium on the reactant side, and we have 2 now on the product side. So we will need to double the calcium sulfate on the reactant side of the equation. And that gives me 2 SO4s, since those coefficients go through the entire molecule or compound. And that worked out quite well, since I have 2 SO4s and PB SO42. So this equation is balanced as well. With C3H6 and oxygen making CO2 and H2O, I start with 3 carbons on the left, so I'm going to have 3 carbons on the right. I'm now down to hydrogen and oxygen, and I would go ahead and do hydrogen first, since oxygen is in 2 compounds on the product side. I have 6 hydrogens on the reactant side. I have 2 on the products. 2 times 3 would give me 6, so that one made it a little bit straightforward. At this point, I have to figure out the oxygen counts. I have 6 in the 3 CO2s, and I have 3 in the 3 H2Os, which gives me a total of 9. And the only way I can get 9 out of 2 oxygens is to multiply it by 9 halves. So that 2 times 9 halves would give me my 9. I can't have a fraction of a molecule. I either have to have one or not. So although this is indeed a balanced equation, to get this to have the lowest possible whole number coefficients, I'm going to need to double the 9 halves oxygen. And if I double one part of a balanced equation, just like in math class, if you change one part of an algebraic expression, you have to change all parts by that same factor. So I'm going to double the 9 halves to 9. I'm going to double the 1 C3H6 molecule to 2. I'm going to double the 3 CO2 molecules to 6, and the 3 H2O molecules also to 6. So now I have 6 carbons on both sides, 12 hydrogens on both sides, and 18 oxygens on both sides. So this too is a balanced equation. So we're going to do 2 examples with words that you have to write formulas for first and then balance. So this first part is just using the nomenclature. We've got lead 4 nitrate. Pb is lead. It's got a charge of +4 with the Roman numeral. Nitrate is polyatomic, it's -1. So when I cross my charges, I have 1 Pb for 4 NO3s. NO3 does need to be in parentheses since I have multiple units of that polyatomic. And now I have an and, which is going to be my plus sign, calcium sulfate. Calcium is in group 2, it has a +2 charge. Sulfate is SO4 -2. The +2 and -2 cancel out to make CaSO4. Next I have lead 4 sulfate. We just talked about how lead is +4. Sulfate is SO4 -2. So we have a +4 lead and we have a -2 sulfate. So we actually just need 2 of the sulfates to balance out the lead charge. So we put SO4 in parentheses with a little 2 after it. If you had just written it as Pb2 SO4 4, you would have ended up having coefficients twice as large as what you actually needed. And then finally we have calcium nitrate. Calcium is +2, nitrate is -1. Cross your charges, CaNO32. So to balance this equation, we have 1 Pb on both sides of the equation. I have nitrate on both sides. I have 4 on the left, 2 on the right, so I'm going to need 2 here with the calcium nitrate. I have 1 calcium on the left. I have 2 calciums on the right, so I'm going to double that there. And my SO4s are balanced now as well. And then my last one we're going to talk about is aluminum metal and nitric acid combined to make aqueous aluminum nitrate and hydrogen gas. So sometimes you're told the forms in which the elements come in and the substances are found, and you could denote those with the S, L, G, and AQ that we've done previously. I don't think that's something I focused on, but I just wanted you to show, see one way that this could be written. When you just have an element, you just write its symbol unless it's one of your diatomics. And I did go ahead and put it in there since we had the information. Metals are solid with the exception of mercury. So I have aluminum, S to begin with. Nitric acid does not have a hydro at the beginning, so it's coming from the polyatomic 8. So that's NO3 -1 and hydrogen's +1. So the 2 charges cancel out to make HNO3. I'm only asking you guys to write formulas of acids that are aqueous, so you could have put an AQ after that if you would have liked. You are told that you have aqueous aluminum nitrate. Aluminum is in group 13. It has a +3 charge. Nitrate is NO3 -1. The +3 and the -1, when they are crisscrossed, gives me AlNO33, and that would also have been aqueous, so I'm thinking I just did it with aluminum. Sorry about that. And then, and hydrogen gas. Hydrogen is a diatomic molecule, so I would write it as H2. And so at this point, I have my formulas written correctly. It's really important to take your time to write those correctly because balancing can be a bit challenging if you don't. When I look at this to balance it, I see I have 1 aluminum to begin with on both sides of the equation. I have 1 hydrogen on the left and 2 on the right. I have 1 NO3 on the left and 3 on the right. So if I first take care of the hydrogens by doubling the H's over there, I now have 2 NO3s on the reactant side, and I have 3 NO3s on the product side. Well, 2 and 3 are not equivalent, and the next number they have in common is 6. So I would need to multiply the 2 by 3 with the HNO3 to get it to 6. And I would need to have 2 of the AlNO3s to bring that nitrate quantity also up to 6. Because I now have 6 hydrogens, I'm going to need more hydrogens on the product side. And I have more aluminums, so I'm going to need 2 more aluminums on the reactant side. Alright, so hopefully this will help you with this particular section of your review.